In 1901, the English philosopher and mathematician Bertrand Russell discovered a problem, a paradox, at the heart of mathematics and all of science. The paradox specifically concerns a foundational branch of mathematics called set theory. So, in this lecture, I teach you all of set theory in like 8 minutes, and then I show how the paradox arises. Russell himself and many other mathematicians thought that they could solve this paradox, but I argue that they can't, and they don't. So let's get started. What is a number? Take, for example, the number 4. I'm not talking about 4 potatoes, or 4 tomatoes, or 4 hairs. I'm talking about the number 4 itself. We know lots of things about the number 4, like that it is evenly divisible by 2, and that it's the square root of 16, I think. I'm talking about the number itself. And I'm also not talking about this right here. This is not the number 4. This is the Arabic numeral written on a piece of glass, the Arabic numeral that represents the number 4. We have other numerals that represent numbers like this one. That's the Roman numeral 4. We use it for counting Super Bowls here in the United States. The number itself is something that no one has ever seen or touched, but we seem to know things about, and also it, and every other number, is essential to science, technology, and all of human life. Immanuel Kant was a Prussian philosopher living in the 1700s. This painting of him was actually done in color, but I've changed it to black and white to make it seem even older. He thought that mathematics was a construction of the human mind. And if that's right, then mathematical truths are, in some sense or other, subjective. But the German and English philosophers Gottlob Frege and Bertrand Russell didn't like this. They thought that mathematics had to be objective. To refute and counteract Kant's view, they developed a view called logicism. According to logicism, mathematics is a branch of logic. And the most basic type of math, which is arithmetic, could be reduced to just first-order basic logic and set theory. I'll explain what set theory is in a second. They thought that if they could succeed in reducing arithmetic to logic and set theory, then they would be able to answer this question, what is a number? And the answer would be that numbers are sets. Okay, well, what is a set? A set is a collection of objects. The branch of mathematics that studies sets or collections of objects was invented by the Russian-German mathematician Georg Cantor in the 1870s. Cantor proved that some infinities were larger than other infinities. Yes, that's right. The idea is that you could have an infinite number of something and then an infinite number of something else, but that you'd have more of one than the other. Yes, it's wild. In order to do this, he had to invent set theory. And so now, I'm going to teach you set theory very quickly, but then set theory is going to run into a terrible problem. It's going to seem terrible. They're going to try to solve it, but then I'm going to show that they didn't really solve it. The version of set theory that I'm going to explain to you in the next few minutes is naive set theory. It's called naive just because it's the ordinary set theory that we can formulate in ordinary languages like English, and it's contrasted with formal or axiomatic set theory, which is formulated in an artificial logical language. You don't have to worry about any of that. A set is a collection of objects, like the set of these markers. There are 3 markers here, and the set of these markers contains 3 items within it. But the objects in a set don't need to be collected together in space or time in order to be a set for the purposes of set theory. So on the one hand, we could have the set of those 3 markers, but we could also have the set of all of the people watching this video, who are spread out all over the world. Maybe they're spread out throughout time. Moreover, the objects in a set don't need to be related to each other in any significant or meaningful way. Another set could be the set of LeBron James, the 4-time NBA champion, and the top half of the Eiffel Tower. These things have nothing to do with each other, really, but we have a set with those 2 things in them, those 2 members, those 2 items. Anything that we can refer to, anything that we can imagine, that can be in a set. We could have a set that consists of LeBron James, the 4-time NBA champion, and Harry Potter, the young wizarding boy who does not exist. That set contains those 2 objects, one of which has won an NBA championship 4 times as of the recording of this video, and the other one is a non-existent boy with magic powers. Indeed, sets can even include objects that can't be imagined. We could have the set of all objects that cannot be imagined. That's a set too. And it contains many, many things, perhaps an infinite number of things, things that can't be imagined. You see these squiggly brackets? The squiggly brackets are used in set theory to pick out the set. And all the stuff inside those brackets are the stuff in the set. So this is the set of LeBron James and the number 4. There are two things in this set, a number and a basketball player. On this form of notation, in order to pick out a set in writing, we would have to write out all of the things that are in that set. But that's too clumsy if it's a big set, like the set of all cats. The set of all cats includes many, many things, too many cats to list out. And also, we don't even know all the names of all the cats in the world, all the cats in the universe. So instead we use this notation, which is read as follows: the set of all x's such that x is a cat. That's called the set builder or intentional notation. You don't have to remember that. The other crucial thing is the word contains. We say that a set contains all of the objects that are members of that set. So this set from before contains LeBron James and the number 4. The set of all cats contains Garfield and all the other cats as well. A set is a many that allows itself to be thought of as a one. Georg Cantor never said that. Someone just said that he said that, but he didn't really say it. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. He did really say that, but he said it in German. When Cantor invented set theory in the 1870s, he wasn't just making up a mathematical game for the sake of it. No. We deal with sets every day. Suppose that someone says that pile of potatoes is enormous. They're not talking about the individual potatoes. They're not saying the individual potatoes are enormous. Some of them may be quite large, but some of them are small, like fingerling potatoes. I'm gonna try to find a photo of a fingerling potato or some other kinds of potatoes. Anyway, when we say that that pile of potatoes is enormous, we're talking about the pile, not the individual potatoes. And we do the same thing with objects that are not collected together spatially. The world population of cats is enormous. The cats aren't collected together in space, but we're talking about all of the cats as a whole, and we're saying that that population is enormous. We're not saying that the individual cats are enormous, although some of them might be quite hefty. The paradox, the logical problem that Russell discovers in 1901 concerns one or more of the rules of set theory. So let's go through some rules real quick before we can get to the paradox. Rule number 1, unrestricted composition. That just means we can make any sets we want. Any set that you can think of, that's a set. In the formal axiomatized version of set theory, this is called the axiom of unrestricted comprehension. You don't have to remember that. Rule number 2, set identity is determined by membership. What does this mean? It means that what makes a certain set, the set that it is just what's inside of it. It doesn't matter how we label that stuff. It doesn't matter how we label the whole set as a whole. All that matters is what's in the set. In formal axiomatized set theory, this is called the axiom of extensionality. You do not have to remember that. Rule number 3, the order of elements in a set doesn't matter. Here, for example, are two sets: the set of the number 1 and the number 2, and the set of the number 2 and the number 1. These two sets are the same set, because the order that you put the items in, the objects, it doesn't matter. Now you can see this rule, this really comes from number 2. Number 2 says that set identity is determined by membership. All that matters is who's a member, or what items are a member of the set. It doesn't matter the order. Rule number 4, repeats don't change anything. This set right here, which contains the number 1, the number 2, and the number 2, is exactly the same set that we were talking about 5 seconds ago. It's the set of just the numbers 1 and 2. If you repeat a number or a member of a set, it doesn't change the set because set identity is determined by membership. That's rule number 4, which is really just derived from rule number 2. Rule number 5, the description of the items in a set doesn't matter. For example, the set that contains just LeBron James and the set that contains all X's, all things, such that that thing is the NBA all-time scoring leader, playoffs included. I'm including the playoffs. If you only talk about the regular season, then Kareem Abdul-Jabbar, as of this recording, is still the all-time points leader. But if you include regular season and playoffs, then it's already LeBron James. Those two sets are the same set. It doesn't matter if you describe him as LeBron James or King James or the NBA all-time scoring leader. Either way, it's the same set containing the same one item in it, and that's that guy who's a basketball player. Rule number 6, the union of any two or more sets is itself a set. This rule just means that if you take two sets, like the set of all cats and the set of all dogs, and you combine them, and then you've got the set of all cats and dogs, well, that's a set too. This rule, number 6, comes from rule number 1, because rule number 1 says you can just make any sets you want. So if you got two sets, and then you put them together, that's another set. You can make that one too. Rule 7, any subset is a set. A subset is just a set containing some of the items that are contained in another set. And that comes from rule 1 too. If you can make any set, then any set you've got, well, any group of those items in there, that's a subset, that's a set too. Rule 8, a set can have just one member. This set contains one item or one element, and that is LeBron James, 4-time NBA champion. A set with just one member is called a singleton set. One important thing to notice is that this set, this singleton set, is not the same as LeBron James. LeBron James is a 4-time NBA champion. This set, the singleton set containing LeBron James, is a 0-time NBA champion. It has never won an NBA championship, and it has never played a game of basketball because it is a set. This rule, rule number 8, also derives from rule number 1. If we can make any set that we want, well, then we can make a set with just one item in it. Okay, we are approaching the point where one of these rules is going to generate the paradox. It's going to blow the whole thing up. Hold on, it's coming. Rule number 9, a set can have no members. This set is called the empty set. You can write it like this with just the squiggles and nothing in between, or you can signify it with this, which is like a 0 with a line through it, which means nothing. This is an empty set, the empty set, or it's called the null set. The fact that there can be such a set just derives from rule number 1, unrestricted composition. You can make any sets you want, including a set with nothing in it. But it is derived from number 2, that set identity is determined by membership, that there's only one empty set or only one null set. That one set with nothing in it, it's defined by the fact that it has nothing in it. So if you have two sets and they're both empty, they're the same set, the null set. Now things get juicy. Rule number 10, you can have sets of sets. This just follows from number 1 as well. If you can make a set out of anything that you can think of, well, you can think of sets too, can't you? Sets can have sets in them. For example, the set of all singleton sets, you'd write it like this, which reads, the set of all x's such that x is a singleton set. That is a set of all sets. It contains the set that just includes LeBron James. It contains the set that just includes the number 17. It does not contain LeBron James, because this is the set of all singleton sets, and LeBron James is not a singleton set. He's not a set at all. He's a 4-time NBA champion. Or you could have the set of all sets, the set of all x's such that x is a set. This, by the way, is how Frege and Russell answered that question from before, what are numbers? They thought, at least they thought until Russell's paradox just blew the whole thing up, they thought that the number 1 just is the set of all singleton sets, the set of all sets with one member. And the number 2 just is the set of all sets with 2 members. Now you might be thinking, I can't wrap my head around this. What does it really mean for the number 4 to just be a certain set? What does that really mean? Don't worry, no one really understands what that means. Not really. Anyway, it doesn't matter because the whole thing is going to be blown up right now with the next rule, which is rule number 11. Sets can contain themselves. This one's weird and it's going to give us the paradox, but that just comes from rule number 1 also. If you can think of it, you can throw it in a set. And so you can think of sets, and so you can throw sets in themselves. Consider, for example, the set of all cats. Does that set contain itself? No, because that set is not itself a cat. It's a set, and everything in it is a cat. So it does not contain itself. What about the set of all sets? The set of all x's such that x is a set. Does that set contain itself? Yes. That set contains all the sets, and it is itself one of those sets, so it contains itself. Or the set of all the things that I'm thinking about. This set doesn't usually contain itself, but right now it does, because right now I'm thinking of that set. Let's follow the pattern of thought that Russell was following in 1901 and 1902 when he discovered this paradox. He was just thinking about and developing this idea, rule number 11, that sets can contain themselves. Think about all the sets that do not contain themselves. The singleton set with just LeBron James. Does it contain itself? No, because it just has one thing in there, and that's LeBron, not any sets, let alone itself. The set of all cats doesn't contain itself, because it itself is a set, not a cat. The set of all singleton sets, does that set contain itself? No, because there are a lot of singleton sets. And so the set of all singleton sets has a lot of sets in it. And so it is itself not a singleton set. It's got many, many members, many, many items in it. And so it doesn't contain itself. And then here are some sets that do contain themselves. The set of all sets, that contains itself. The set of all non-singleton sets, yeah, that set contains itself because there are many non-singleton sets. And so that set, the set of all non-singleton sets, has many members, and so it's a non-singleton set. So because that set meets its own condition, it is inside of itself. Or the set of all sets that have been mentioned in this room which is an endless black abyss from which I am speaking to you right now. Up until right now, that set did not include itself, but I just mentioned it, so now it does. Here's the next thought that Russell had in England in 1901. Okay, let's take all those sets that do contain themselves, let's collect all of them together and make another set out of them, the set of sets that contain themselves. Now we've got a set of those. We'd write it like this: the set of all x's such that x is a set that contains itself. Now let's take all of the sets that do not contain themselves, collect them together, make a set out of those. Russell thinks to himself in 1901 as he's barreling toward a paradox that's going to blow up the whole project to form the foundation of mathematics and all of science. This set that includes all of those is the set of all sets that do not contain themselves. And we'd write that like this: the set of all x's such that x is a set that does not contain itself. And then something happened. He realized a problem, and he wrote this problem in a letter in 1902 on June 16th to Frege. And Frege received the letter. This is what the letter really looked like. Frege got the letter, and it broke him. Physically, he had a breakdown and had to be hospitalized upon reading this 2-page letter. And the letter asked this question: the set of all sets that do not contain themselves. This set, does it contain itself? Here it is again. The set of all x's, the set of all things, such that x is a set that does not contain itself. Does this set contain itself? Well, let's go through both possibilities. If it does, then this set is in here, it's in itself. And the only way to be in there is to meet this condition, the condition of not containing oneself. So if this set does contain itself, well, then it meets this condition, and this condition says that it doesn't contain itself. If it does contain itself, then it doesn't. And consider the alternative possibility. If it doesn't contain itself, then it meets the condition. It's a set that doesn't contain itself. So if it doesn't contain itself, it meets the condition, and then it's in there, which means it contains itself. So if this set doesn't contain itself, then it does contain itself. If it doesn't, then it does. And if it does, then it doesn't. So this set both contains itself and doesn't contain itself. And that's just a contradiction. So set theory doesn't work. That's the paradox. Now you might be thinking, oh, okay, well, that's no problem. Set theory was just some made-up rules, right? That's how math is. We just make things up. Axioms are stipulated, which is to say made-up claims. So we just made up all these rules, including Rule 10 and Rule 11. And Rule 11 is really the source of the paradox. Once you let sets contain themselves, well then, you're going to be able to formulate this set, and this set is the one that leads to the paradox. So let's just change the rules, right? Yeah, that's exactly what Russell tried to do. He tried to just change the rules of set theory. He made up some new rules, and according to his rules, sets cannot contain themselves. And that's what other mathematicians doing set theory have done, like the Zermelo-Fraenkel set theory. That's a version of set theory with some restrictions. They just get rid of Rule 11. And of course, if you get rid of Rule 11, you say that sets cannot contain themselves, well then you also have to get rid of Rule 1. Unrestricted composition, or the axiom of unrestricted comprehension, or whatever you want to call it. So that's what all the mathematicians do. But does that work? Like, can we just change the rules? Back before, when we were going through all those rules, Rule 1 and Rule 2 and all the way up to Rule 11, were we just making up the rules? No, we didn't just make up the rules. And so we can't just change them. That was me. I just said that. What I'm going to argue for the next, 2 minutes, is that the rules of set theory are not made-up rules. They're real, non-made-up, objective rules that already exist, and they govern perhaps one of the most fundamental practices of human existence, and that is predication. Now I have to teach you some linguistics. This is going to take, 60 seconds, 90 seconds, something like that. Once I've done that, I'm going to regenerate Russell's paradox and show that it was never a paradox just for set theory. It's a paradox for all of language and thought itself. Let's go. Here is a sentence. Garfield is a cat. It contains 4 words. Grammatically speaking, though, it has 2 essential parts. It has this first part, which is called the subject of the sentence, and it has this second part, is a cat, which is called the predicate. The subject is what the sentence is about. It's about Garfield, the cat. And the predicate says something of Garfield. It says that Garfield has a certain characteristic, and that characteristic is being a cat. LeBron is the subject of this sentence. He's the thing that the sentence is about. And Dunks, here we go, is the predicate. We can say that predicates are true of certain subjects. So the predicate is a cat is true of Garfield, and the predicate Dunks is true of LeBron, and it's not true of me. What was the relationship between sets and objects? The relation was containment. Sets contain objects. The objects are in the sets. What is the relation or the relationship between predicates and subjects? Being true of. Predicates are true of, or a predicate is true of, a subject. What I'm going to do now is I'm going to leverage this similarity to try to regenerate Russell's paradox, but now it's not with some made-up rules of set theory, but with some very much not made-up rules of predication. And predication, let me just remind you, is just the practice of saying things about things. So the practice of predication is ubiquitous. It is utterly widespread. We do this constantly. We do it linguistically all the time out loud, and almost every thought we have predicates something of something. Remember rule number 1, unrestricted composition? For set theory, that rule was the rule that there's a set for any imaginable collection of a thing or of things. Well, that rule seems like it just is true of predication also. There is a predicate for any imaginable characteristic of a thing. Anything that you can say about something, there's a predicate for that. Of course there is. And those rules of set theory that allowed Russell in 1901 to generate his paradox, those rules of set theory, the relevant ones, they're just true of predication too. Rule number 10 of predication. You can predicate things of predicates, just like you can have sets of sets. Well, that's true. You can predicate things of predicates. Here's a perfectly grammatical English sentence. Is a cat sounds funny. Yeah, sure, kind of. It does kind of sound funny when you think about it. Is a cat, is a cat, is a cat. Sure, it sounds funny. In this sentence, the predicate is a cat is functioning as the subject of the sentence. Sounds funny in this sentence is the predicate, and it's saying something about the subject, which is the predicate is a cat. Sure, we can do that. That's a perfectly meaningful thing to do in any natural language. We can predicate things of predicates. Yes, we can. Can you smell where this is going? Predicates can be true of themselves, just like sets can contain themselves. Is this right? I think it is. Consider, for example, the sentence, is a cat is a cat. Is that true? No, because is a cat is a predicate. So it doesn't have a tail, it doesn't have fur. Is a cat is not a cat. But what about this one? Is a predicate is a predicate. Yes, that's true. Is a predicate is a predicate. It is. And that's a case where the predicate is a predicate is true of itself. It says of itself that it's a predicate, and it's right. So, rule number 11, predicates can be true of themselves. Some predicates, of course, are not true of themselves. Like is a cat, we already saw that. Is a cat is not a cat, so that predicate is not true of itself. Dunks. Dunks doesn't dunk. Dunks is a predicate, so it can't play basketball, it can't dunk. So it's not true to say that dunks dunks. No, false. Tastes like chicken. That's a predicate. Something can taste like chicken. Does taste like chicken taste like chicken? No, it doesn't. Taste like chicken is a predicate, so it doesn't taste like anything. But then you've got plenty of predicates that are true of themselves. Is a predicate, so is a predicate is true of itself. Is a string of words. Is a string of words. Yes, it is. So that predicate is true of itself. Typically comes at the end of a sentence. Well, typically comes at the end of a sentence does typically come at the end of a sentence. So that predicate is true of itself. Now, let's try to make a predicate that is true of all of the predicates that are true of themselves. And that predicate just is true of itself. Is true of itself is true of all of the predicates that are true of themselves. Fine, nothing wrong with that predicate. But then, what if we tried to make a predicate that's true of all of the predicates that are not true of themselves? That predicate would be is not true of itself. And now we're going to generate the paradox. I can't write this in a letter to Gottlob Frege because Gottlob Frege is dead, but I'm writing it in a video to you. Here's the question. Is not true of itself. This predicate, is it true of itself? Let's go through both possibilities. If it is true of itself, well then, what does it say about itself? It says that it's not true of itself. So if this predicate is true of itself, then it's not true of itself. If it is, then it isn't. What about the alternative? If this predicate is not true of itself, then it's not true of itself. But then it meets the condition set out in itself. It has this characteristic specified by the predicate. It's not true of itself. So if it's not true of itself, well then it's true of itself. If it is true of itself, then it's not true of itself. And not true just means false. So if it is true of itself, then it's false of itself. And if it's false of itself, then it's true of itself. So it's both true and false, which is a contradiction. And this isn't a paradox that we can just escape by declaring that there is no Rule 11. In the case of set theory, yeah, maybe we could just declare that sets cannot contain themselves. But in the case of predication, which is just talking, in the case of saying things about things, we can't just declare that predicates cannot be true of themselves, because they can. This Rule 11, this just is true. And once you give me Rule 11, I'm going to generate the paradox. This is a paradox that we can't escape.